Bueno, vamos, tomen sus asientos, así podemos comenzar con la sesión de la mañana, the last session on stellar structure and evolution. And, bueno, we start immediately. Our first speaker no habla español, así que, pero igual la presentamos en español. Ella es Annie Rathsam, and she will talk us about lithium depletion in solar analogs.
Okay. Hi, everybody. I'm Annie Rathsam. I'm a PhD student at the University of São Paulo in Brazil. And my work is on the age, mass, and planet effects on the lithium abundance of solar-type stars. So lithium is a very important element for stellar astrophysics because it is depleted at a relatively low temperature of about 2.5 million Kelvin. And in main sequence solar-type stars, the temperature at the base of the convection zone only reaches about 2 million Kelvin. So since the standard stellar model does not consider any type of mechanisms of transporting material that is in convection, this means that the lithium abundance should be constant over time for this type of stars in the main sequence. However, what we observe is that the stars present a smooth decay of their lithium abundance with age, which indicates the existence of non-standard transport mechanisms. Many non-standard mixing processes were invoked so far to try to explain these observations, such as convective overshooting, the atomic diffusion, gravitational settling, rotation-induced mixing, and the mixture due to gravity waves. But so far, no model has been able to explain simultaneously every characteristic regarding lithium abundance in different types of stars. Based on this, our goal with this work was to determine, besides age, which other factors affect lithium abundance and quantify the dependence of lithium abundance with these other parameters. With this, we are contributing with data for the development of non-standard stellar interior models. Our sample was composed of 74 nearby solar twins and analogs, plus 79 solar twins from a previous work from Marilia Carlos and collaborators. We selected only bright stars, so our cut in magnitude was magnitudes below 10 meg. Our stars have roughly a solar metallicity within minus 0.15 and 0.15 dex. And they have masses between 0.85 and 1.1 solar masses. Our spectra were observed with HARPS and are taken from ESO's public database. We queried for individual spectra with signal-to-noise ratios ranging between 20 and 370 to avoid individual noisy spectra and saturated spectra. And for each star, we combined the spectra to reach a final spectrum with a signal-to-noise ratio between 270 and 1,000, which allows us to perform our measurements with a high precision. We performed the Doppler correction using IRF and the radial velocity information from the HARPS header files and normalized our spectra using IRF. To find the stellar parameters, we measured equivalent widths from iron lines, again using IRF, and determining the continuum individually for each line. We adopted the differential spectroscopic method using the sun as a reference star with spectra reflecting on the surfaces of Vesta and the moon. With this, the effective temperature, surface gravity, and metallicity were found using the differential spectroscopic equilibrium with the code Q2, and we have here on the left an example of the spectroscopic equilibrium. Our ages and masses are the most probable ages and masses from a probability distribution calculated again using Q2, and the way that Q2 calculates this probability distribution is by comparing our observed spectroscopic parameters and theoretical parameters from Yonsei-Yale isochrones. So we use our temperature and metallicity determined spectroscopically. Our absolute magnitude is from V magnitudes, and we also use parallaxes from the third Gaia data release. To determine the lithium abundances, we performed the spectral synthesis of the lithium line near 607,007.8 angstroms, with the mu code, and we perform NLTE corrections with the inspect database. We find typical errors of about 6 Kelvin in effective temperature, 0.02 dex in log G, 0.01 dex in metallicity, 0.4 gigayears in age, 0.01 solar masses in mass, and 0.04 dex for lithium abundance. we expected to see in our results a strong lithium abundance versus age correlation, which would be consistent with what is found previously from other works. And we also expect to see some correlation between a low lithium abundance and a low mass, because both low mass and also metal-rich stars present deeper convective envelopes. So we expect that these stars are able to deplete more lithium than stars that have shallower convection zones. So this is our sample. Here we have the lithium abundance versus age, color-coded by metallicity. And we can see that there is a very strong lithium abundance versus age correlation in here. And since our stars have a very small range in metallicity, we can't really see the effect of metallicity. This is better explored in the work from Julia Matheus et al. And they report that metal-rich stars have lower lithium abundances, which is consistent with what we expected based on their convection zones. For our solar twins, we find a relation between lithium abundance and age with a very high significance of about 14 sigma. And this improves what was found by Marilia Carlos, which she found a dependence of only 10 sigma, which already was a very strong correlation. In here, we have our lithium abundances plotted against mass on the left and the ratio of convective mass over mass on the right, both color-coded for age. And we can see that there is a tendency for low mass stars to present lower lithium abundances and higher convective mass stars. But in both cases, the correlation with age seems to be more important. To quantify the dependence with these parameters, we fitted the residuals of a relation found for solar twins using our entire sample, and we found a dependence of 2 sigma for mass and 5 sigma for the ratio of convective mass over mass. Another thing we can ask ourselves is whether planet hosts are more lithium depleted, and this would make sense because lithium is a refractory element, and this means that it could be used to form the rocky material of planetary systems. And this means that the star is formed with less lithium. This is something that was already searched in the literature, but we have many conflicting results. So we select from our 192 stars, we found that 35 of those plus the sun had confirmed orbiting planets, and we compared the lithium abundance of these stars with the median and average lithium abundance of twin stars. That were stars that had the same age within 0.5 gigayears, the same mass within 0.1 solar masses, and the same metallicity within 0.2 dex. This is because all these parameters really affect lithium abundance. So to do this comparison, we need to select stars that are very similar. And what we find is that planet hosts are more lithium depleted by about 0.2 dex with a very high significance above 99%. We also tested different bins in mass, age, and metallicity for the twin stars. And in all the cases, we find a very high significance. Our lowest significance found was of about 83%, which already points towards a very important correlation. So to conclude, in our sample of 151 solar twins and analogs, we find a strong lithium abundance versus age correlation, which has a significance of about 14 sigma in the case of solar twins. We also find that mass and convective mass affect lithium abundance, but are less important than age. And planet host stars present lower lithium abundance with a very high significance. All these results were already published in a paper in the monthly notice of the Royal Astronomical Society. This QR code takes you directly to it in the archive. And if you have any questions, you can ask me or send me an email. Thank you.
Bueno, gracias a Ani. Tenemos un montón de tiempo para preguntas.
Beautiful work. What about stellar rotation and stellar activity? Have you comment about this, please?
Yeah, these are parameters that I believe rotation affects lithium abundances, but we didn't explore rotation and magnetic activity.
Are you going to?
We don't intend on, but it's something that we could do, yes.
¿Más preguntas, questions, comments? No.
Hey, how young are your younger stars in the sample?
Here we have the stars that I think they start at about 0.5 gigayears, something like that. Yeah.
Da hora o trabalho. Anne, nas estrelas que você encontrou uma correlação com o planeta, você encontrou alguma correlação com a depleção de lítio e a massa do tamanho do planeta em questão? Dos planetas?
A gente não explorou os parâmetros do planeta.
Tá.
I think the one I wanted to ask was the same. Is about the mass of the planets?
Yeah, we
Okay.
didn't.
And do you think the lithium controversy is solved?
Oh no.
What
Okay, we
can
have-
be what can go wrong then?
No, we have this.
Which she mentioned a controversy, right?
The planet controversy.
Yeah, the connection with the lithium.
I'm not gonna say anything that important. I think we have an indication of something, but yeah, we need more works on that. Another results confirming what I found.
Can you describe how you measure this significance in the two samples?
We
You
performed
went
it-
through the difference in abundance for planet hosts and non-planet hosts. It's just did you
This graph?
there?
you need-
Yes.
Oh, okay. We are plotting the lithium abundance of the planet minus the average or median lithium abundance. I didn't say in the graph which points were which, but the light blue is median and the dark blue is average or the opposite. And these two lines show the median of the medians and the average of the averages. And in both cases, they are below zero. So this indicates that planet hosts are more lithium depleted. Okay.
Okay, and the significance?
It was a t-test.
Thanks.
Thanks. Since you have ages and you have, I assume that the sample of these stars is relatively nearby stars.
Yeah.
Right. So they should have Gaia, like exquisite phase space information. Can you track back to the origin of those stars, the lithium, I don't know, correlation function spatially in the solar neighborhood? And see if there are any correlations of you have a lot of scatter in this age versus lithium overabundance plot. I mean, there is lots of information in there. I wonder if there is a spatial correlation to some degree that you can pull out.
Yeah, we didn't do it, but it's something we could do, yes. It would be interesting.
Okay. Then any more question or comment? No, then we thank Annie. And we move on to the next talk. Our next speaker is Matheus Castro. Yes, and nos va a hablar, his talk is titled Multiple Element Abundance Fit Software.
Okay, so bom dia, buenos dias, good morning. Thank you. Also, buongiorno, bonjour, guten tag. Okay, so I'm going to give a sneak peek about the software that I'm developing my master under the supervision of Dr. Beatriz Barbuí in the University of São Paulo in Brazil. And the software is the Multiple Element Abundance Fit Software, or for the closer ones, the MEAFS. So what is MEAFS? MEAFS is a software to derive chemical abundances in spectra and is independent of the wavelength. MEAFS can perform numerous fits for lines and spectra in a single run and can derive the abundances for the elements and for hundreds of lines in a couple of hours. For now, it uses the turbo spectrum to generate the synthetic spectrum, but we also intend to include the pfund in the code as well. And most important, MEAFS is open source, is already published in my GitHub page, and is written in Python 3 and C language. Okay, but you may be wondering, why MEAFS? So MEAFS uses modern features like Python 3, and because of this, it's compatible with all type of device. With this, I mean, you can install in a Linux, in a Windows, in a Mac, or even an Android. You just need to run Python. And it's easy to install. For now, you can install using git clone from my GitHub page, but the goal is to include MEAFS in the apt, pacman, snaps, and pip package managers. And MEAFS will have two operating modes. The first mode is an independent run. So you open MEAFS, put your line list with the lines that you want to solve, to fit the abundance, and then it will run. But also it will have a second and optional way to run it, because after the fit, you can change manually the parameters of the input and also the abundance, the continuum, the output parameters. Okay, and what we have so far, as I said before, MEAFS is already published in my GitHub page, and the code is working and performing fits. The first results can be seen in Hernandez et al., a paper from this year in the monthly notes. And for now, it's automatically fitting the lambda shift, the continuum, the convolution, and the abundance for the needed lines. And the way MEAFS do this is applying the chi-square analysis to find the difference between the lines, and in a combination with the Nelder-Mead method to minimize this difference. And the way that the Nelder-Mead method works is running the synthetic generator spectra a couple of times, a lot of times, and trying to minimize the difference between the two curves. Okay, but not only that, MEAFS is also capable to give first results. You have your all analyzation process, but as an output, you can also have the like a CSV ASCII file with the abundances of your data. But not only for the lines, for already included the elements abundances, the mean, and all the analysis for the elements itself, and also gives like read to publish plots. For example, this one is a plot for the Hernandez et al., and here is for the Lantanium 2 line. And we have the data points. The blue curve here is the best fit, the area of varying 0.1 in the abundance, and also, for example, the no lanthanum at all. Just as another example, this is a thorium 2 line and is the same plot. But I can also have this box plot here, and me personally, I think this is very interesting because here in a single plot, you can have all the abundances analysis for your star or for your object. So you can have the confidence level, the max mean, the quartiles, the outliers, and this is already included in MEAFS. So if you run the analyzation part, you get all of this just quickly. But not everything is perfect. MEAFS has also some problems, and the most difficult problem now is because I want MEAFS to be independent of the wavelength. With this, I mean I want to include a lot of different synthetic generators, because single synthetic generator software it's more efficient in a certain range of wavelength. So I want to include a lot of them to be able for the MEAFS to be independent of the wavelength. And to do this, I need to include like modules to do the correspondence, to talk with MEAFS, to talk with the generated synthetic, and the other way. And this is not a hard work, but it's a work that takes a lot of time. So if I want to include all this, take a lot of time. Not only that, for now, the continuum fit is not well fitted in crowded regions, because in crowded regions, the continuum goes a bit down. And even if I take a large range of wavelengths to try to fit the continuum, it's not working the way I want to. And for blended lines, the abundance fit is not so satisfactory. And I need also to work on this better. Okay, so the next steps are, that's where I need to include the XVII software, because XVII is a code, written by Dr. Trifon Trifonov in the Max Planck Institute for Astronomy in Germany. And it's a code to analyze exoplanets data. And also is a software written in Python 3, but with Fortran. And I had the opportunity to work with Trifon this year. And I want to MEAFS to apply the same way that XVII works. Because when you open XVII, you can put your data, and here, for example, you can change the parameters of your input, the parameters of your output, and check how well fitted the curve is. And I want to apply this to MEAFS as well. To do that, I need to develop a graphical user interface, or a GUI. And this is a step that I intend to do until the end of my master. Okay, so to summarize it, MEAFS is a working code, and you can perform fits, you can find abundances in spectra. And for now, it only uses the turbo spectrum, but there are working processes to include other synthetic generators. I still have some problems with the continuum fit in crowded regions and the abundance fit in blended lines. That's also why I want to develop a GUI to help the experience of the user, to help the fit process. And I need to find a better way to fit this, and in addition with the user. And a GUI needs to be developed to help through this analyzation process. And that's all. Here you can find the QR code to my GitHub page. Thank you.
Gracias a Matheus. Any question?
Oi, Matheus.
Oi, professor.
Incrível o teu trabalho, parabéns. Tô com duas dúvidas. Você falou que está rodando com o Turbo Spectrum, mas não ficou claro para mim quais os modelos de atmosfera que são utilizados. E a segunda pergunta é qual que é a resolução espectral mínima que você considera que o observado precisa ter para o MEAFS funcionar bem?
Tá. Com relação ao Turbo Spectrum, ele foi testado nesse paper do Heitor, mas o meu objetivo é, como eu quero que seja o código seja abrangente, isso eu vou deixar a cargo do usuário. Então, não sei te dizer, mas isso vai ser a cargo do usuário para setar o gerador de espectros. Então, o MEAFS só vai utilizar o gerador. Então, o MEAFS é independente disso, do modelo. E a outra pergunta? A resolução. Esses espectros aqui têm uma resolução de aproximadamente 20.000, porque eles são até para espectros que estão sendo utilizados para ajudar o QUBES, o desenvolvimento do QUBES, então tem mais ou menos a mesma resolução. Mas assim, não tem uma resolução mínima. Lógico que a gente sabe, se a gente coloca uma resolução muito baixa, a gente não consegue derivar as abundâncias muito bem, inclusive com regiões de blend. mas o método do Q quadrado, ele pode ser aplicado para qualquer resolução. Aí também fica a cargo do usuário, se ele usar um espectro muito baixo, a curva vai estar ajustada, mas quão bem isso representa realmente a abundância também é a cargo do usuário.
¿Más preguntas?
Hi, I don't know, maybe I missed it, but does the spectrum need to be within a specific range or
No, it's completely independent of the wavelength.
of the wavelength? Okay.
You need to pay attention in the synthetic generator spectrum. As I said, some synthetic generators have more efficiency in a certain range, so you need to be aware of that.
Okay, thank you.
Thank you. Nice work.
Thank you.
Did you talk about a convolution parameter? Can that be taken as a? Can you work with fast rotators? That would be the question.
Yeah, I don't know about that. Sorry, but that you can perform the fits, and if the convolution is a problem, you can also set a certain range that you want the convolution to be applied. So you can try a box to like a minimum and max to apply the fit.
Okay. Thanks for your work. It's amazing.
Thank you.
I have just a very brief question. What's the range of effective temperatures that will be ideal for your code to work?
Yeah, as I said, it's completely independent of everything. It depends on the synthetic generator. So when you apply the models to the synthetic to the software that generates the synthetic spectrum, you will also apply the temperature that your star or your object has. So that's why I want the modulus for the MEAFS. So you can choose the best synthetic generator that applies to your work.
Okay, cool. Thank you.
Hi. How much range do you normally work with? For example, 500 Armstrongs, 1,000, 2,000. I mean,
for this
normally, which is you give how much in input to the code?
For this paper from Hernandez, we worked from 3,000 to 4,000 angstroms. But again, you can set your line list and your spectra whatever you want. Thank you.
Ok, le agradecemos nuevamente, Matheus. Pasamos a la siguiente charla. No sé si está Elisson. Elisson Saldanha. ¿Sí? Sí. Está bien. Spanish? No. English. Okay. Our next speaker is Elisson Saldanha da Gama de Almeida. And he will speak us about new insights on weak winds in massive stars from hydrodynamical simulations.
Bom dia, buenos dias, good morning, everyone. My name is Elisson Saldanha Gama de Almeida. I am a postdoc at Universidade Valparaíso in Chile. And in this presentation, I will talk a bit about my work on the colored weak wind phenomenon that happened in certain class of main sequence massive stars. So first, very briefly, advertisement. I have a poster that's very close to here, not about main sequence massive stars, but evolved massive stars, about supergiant stars. So if you are interested about that, you are welcome to visit us. And there are some copies printed in paper that you can bring to home. And the poster will be there up at the end of this afternoon. So massive stars, they born as O-type stars or early B-type stars, and they have what we call as radiative line-driven winds. Here, I show example of a theoretical synthetic spectrum that calculates using the code CMFGene in the ultraviolet region for the parameter spaces of O-type stars. The full model is shown in black, and the line is created by ions of iron, in case iron 3, 4, and 5 are shown in colored lines. The big point of this figure is to say that these lines, they are formed at different locations of the atmosphere. And when I say the atmosphere, I'm considering both the photosphere and the wind region. Here, this bunch of lines, the thin lines created by iron, they are mostly formed in the photosphere of the star. And so they are important to give a net linear momentum to the gas closer to the photosphere. So they are important to start the wind, but they are not enough to have the develop of a line-driven wind. For that, we also need the radioactive acceleration coming from larger distance from the stellar surface. And for that, we have here in the ultraviolet region, the silicon-4 and the carbon-4 lines that are formed in the extended region of the wind, throughout the wind. They are in this model here forming what you call P-signaling profiles. If you observe a P-signaling profile spectrum of a star, this is a spectral signature that this star has a line-driven wind. And by modeling these lines, we are then able to derive the fundamental parameters of the wind as the mass loss rate and the terminal velocity. So why we should care about stellar winds in massive stars? Here I show how the stellar mass evolves with time for a star that's born with 40 solar mass, as predicted by the evolutionary models from the Geneva group. Here the dashed line, the broken line, sets the turn-off point, so the end of the main sequence phase. And we see that this star, since it's born until the turn-off point, it releases to the space about 8 solar mass. And after that, in a very quick time, in comparison with the main sequence phase, this star will release even more mass due to stellar winds, as it's evolved to be supergiant stars, LBV, and Wolf-Rayet star before exploding as core supernova, exploding as core supernova. And so I think that this is a take-home message. Stellar winds are very important during all the evolutionary phase of massive stars. Unlikely low mass stars like the sun, stellar winds will be important to their evolution just when these stars leave the main sequence phase. But for massive stars, stellar winds are important since they are born until they die. Maybe you forget a lot of stuff I will say here, but if you remember this, I think I would be happy with giving this talk. So I will introduce what is the weak wind problem. Here is a diagram showing the measured mass loss rates. By measuring mass loss rates, I mean mass loss rates that are derived by modeling the spectroscopic data using radioactive transfer models. And here we have theoretical mass loss rate from the work of Vink 2000. Despite being published 23 years ago, these mass loss rates are currently used in state-of-the-art evolutionary models because they are very simple to be implemented in evolutionary models. And here we have basically two very different cases. So we have OB supergiants that have luminosity higher than 5.2 DAX. And we have here Lithium dwarfs that have luminosity lower than 5.2 DAX here. And we see that for the OB supergiants, the measured mass loss rates, they agree very well with the theoretical predictions. But when you look to the low luminosity stars, this is not the case. The theoretical predictions predict mass loss rates in the range of 10 to minus 7 solar mass per year, while the derived values, the measured values are in the order of 10 to minus 9. So there are a difference of 2 orders of magnitude between the measured mass loss rate and the theoretical mass loss rate for this type of stars. So the key point of my work about weak winds is to answer what happens between these and these. So what happens with all type stars that have luminosity of about 5.2 DAX? Do they agree with the theoretical predictions or do they strongly disagree with them? So in short, weak winds are found in Lithium dwarfs, where the measured mass loss rates are much lower than the theoretical predictions. In this paper, I analyzed 9 Lithium giants to model the UV and the visible spectroscopic data of them, using NOAA radiative transfer models calculated with the code CMF gene. Why Lithium giant? Because they have numbers close to the value of 5.2 DAX. And with that, we are able to derive the fundamental stellar parameters, the effective temperature, log G, the mass loss rate, and the terminal velocity. Here you focus on the mass loss rate, since that's the parameter that taught directly the weak wind problem. This is just an example of a fit for one of the stars from the sample of 9 stars. The UV and the visible spectroscopic data is shown in black, and the best fit CMFG model is shown in red. We are able to find a fairly good match in both in the UV and the visible region. And here is the same plot that I showed before, comparing the measured mass loss rate with the theoretical mass loss rate from the work of Vink. And here is the difference between them as a function of the stellar luminosity. So we found that yes, Lithium giants, they have weak winds, and they are in a kind of transition between stars with normal winds, in the sense that they agree with the theoretical predictions, and the Lithium dwarfs that have a very large disagreement with the theoretical predictions. And we see that the region of 5.2 DAX luminosity is indeed critical to the weak wind problem. We see that in this region here, we have a transition. Here in 0, there is no difference between the theoretical mass loss rate, and here are the Lithium dwarfs. So I need to skip a lot of things. The point is that all this work has been done using a beta law approximation. So this means that you can put whatever you want, more or less, within readable parameter space for the terminal velocity and for beta. in the CMF gene, and we can put whatever we want for the mass loss rate. But we can play with beta to fit the observations. For example, B supergiants, they require much larger values of beta, up to 2 to 3, to fit that spectra. So the work that I start is to use the code wide wind to solve the equation of momentum of the wind based on the CAK formalism. The big insight of the CAK formalism is to express the line force as a function, the radiative acceleration due to lines as a function of the radiative acceleration by lattice scattering. So this is, I think, that my final plot. Here I show the observed line of one old dwarf star. And here I show the CMFG model using the hydrodynamic predicted by high wind, the fast wind model using the hydrodynamic predicted by high wind, and the fast wind model with a beta law approximation. And we see that both of them reproduce almost the same synthetic line in H alpha. And we are able to derive a value of a mass loss rate that is in agreement with previous values in literature, and that's much lower than the theoretical prediction of Vink. Well, I'll go to the conclusions. Sorry for the time. Thank you.
Okay. Only a short question.
Hi, very nice work.
Thank you.
You said that you also derive the temperatures and gravities for those stars.
Yes.
Can you tell me what is the range of values that you obtained?
Yeah, these stars have a range of effective temperature around 30,000 Kelvin and 35,000 Kelvin, and log G it's about 3.5, 3.6, 3.7.
A very, very short question. Yes.
You're using, I think, 1D models for the winds. Is that something that really needs to be changed to 2D or 3D to explain the discrepancies? Or
yeah, the CMFG model is 1D model, as the Y-wind hydrodynamic simulation is also 1D. This would be an issue if these stars would be close binaries, but this is not the case. So I don't think that these discrepancies that I was saying, they rely due to 1D approximation. It's possible to reproduce very well the spectra of a bunch of Mason-Hov stars using the CMFD models, such as the fast wind, that is also 1D model.
Ok, bueno, muchas gracias a Elisson. Pasamos al siguiente charlista, que es Facundo Moyano. Y él nos va a hablar de... ¿Lo presenta, Facundo?
Hello everyone, my name is Facundo Moyano. I'm originally from Argentina. What? I'm originally from Argentina, but I'm doing my PhD at the University of Geneva in Switzerland. And I work mainly with Patrick Eggenberger and George Spainet in stellar evolution, and in particular in stellar rotation. So first, I would like to stress out why rotation is so important. So the thing is that rotation can transport chemical elements in radiated regions, for example, lithium, and can, in some cases, affect the structure and the evolution of the stars. For example, in massive stars, I show here the HR diagram of a 15 solar mass star during the main sequence for 3 different assumptions about the rotation, the treatment of the angular momentum transport. In black, a track of a non-rotating star in red, a track only with rotation with hydrodynamical processes that we believe we understand, and in blue, a model also including magnetic fields. In some cases, the transport of chemical elements can change so much that the evolution is completely different. This is because, for example, hydrogen is transported to the core, helium is transported to the surface, lithium, nitrogen, or other elements. And so rotation, depending on treatment of the angular momentum transport in the stellar interior, can change the evolution of the star. So the question that we are trying to answer nowadays is how is the angular momentum redistributed throughout the evolution of the stars? So the thing is that nowadays, thanks to space telescopes like Kepler, TESS, and in the future Plato, we have long light curves of stars in different evolutionary phases. For example, this is a light curve of I think it's a red giant of 4 years in time span. And the thing is that if we go to the frequency space, for example, with the Fourier transform, we can study the individual pulsations. And those pulsations, can give us information about the stellar interior. And the thing is that rotation can have a particular effect on the individual pulsation modes that are illustrated here by those peaks. This is the case, for example, what is known as rotational splittings. And by studying those pulsations, we can infer the rotation rate in the stellar interiors. And that can be used to constrain our models. So nowadays, with those techniques, we have rotational constraints of the stellar interior for hundreds of stars in different evolutionary phases and different mass ranges. So this is shown in this plot on the right, where I showed the core rotation rate as a function of the surface gravity and the corresponding evolutionary phase with a theoretical HR diagram. So we have approximately 800 main sequence stars with core rotation rates measured, only 8 to 9 subgiants, more or less 800 red giants in the lower part of the red giant branch, more or less 100 core helium burning stars of low mass, termed red clump stars, and 60 secondary clump stars. Now, if we go to the more advanced phases during the degenerate phase, the white dwarf phase, we also have some measurements of white dwarf stars. And just for completeness, there is other group of stars called hot subdwarfs, which are the result of binary interactions, but we also have constraints for those kind of stars. So these constraints can be used to test our stellar evolution models. So my work consists on studying the angular momentum transport using mainly the stars in these green dots, which comprise only the hydrogen and helium burning phases. And so when we try to compare the rotation rate of the stellar core in stellar evolution models with initial velocities in agreement of the main sequence stars, only including hydrodynamical processes, we always have a disagreement of 2 to 3 orders of magnitude. And it doesn't really depend on the initial conditions of the models. It doesn't depend on the mass, metallicity, nor initial velocity or other input parameters. For example, I show you here other stellar thrusts computed at initial velocities of 0.6 kilometers per second, 6, 60, 120, and 180. The problem with the red giants is always there. And so this led to people to believe and think that we need other physical processes in stellar evolution models to slow down the course. Some of these processes include additional rotational instabilities that don't work very well, internal gravity waves, which are perturbations that arise simply because of the interaction between convective motions, for example, in a star with a convective core, and can trigger waves in the stellar radiative interior that can transport angular momentum and so can change the rotation rates. Other processes that come in different flavors are magnetic fields, large-scale magnetic fields from the star formation, or dynamo-generated magnetic fields. And so I specialize in magnetic fields generated by the Tyler-Sprout dynamo, which is a dynamo that can operate in radiative regions of basically any kind of star, and was first proposed by Sprout in 2002. And the important properties is that it can transport angular momentum very efficiently, meaning that it can change the rotation rate in the stellar interior quite importantly. and it's only triggered by differential rotation. So the schematic way in which this dynamo occurs is illustrated in these red dots, which basically relies on the omega effect, which basically transform radial magnetic fields into azimuthal magnetic fields. And just by the Taylor instability, the regeneration of the radial fields is self-sustained and can amplify the magnetic fields in the stellar interior. So these magnetic fields has been very successful in reproducing different constraints coming from asteroseismology in different evolutionary phases. For example, in the case of the Sun, it has been successful in reproducing the solar rotation profile into radiative regions, which is illustrated by these data points, which were, as I said, obtained by heliosysmic techniques exploiting the rotational splittings. And the two lines just correspond to models including only hydrodynamical processes, which, as I show, don't work, and models including these kind of magnetic fields. Now, moving on to slightly more massive stars, between 1.4 and 2 solar masses, we have a group of stars called Gamma Doradus stars. And in a recent paper, I demonstrated that these kind of magnetic fields can also reproduce both the core rotation rate and the surface rotational velocities, combining so two different techniques. So, namely, spectroscopy to obtain the surface rotational velocities and asteroseismology for the core rotation rate. And this is illustrated in this plot, where I show in total 6 models, including only rotation, so basically no magnetic fields, and models computed including magnetic fields. The black line shows the position of the 0H main sequence, and the thing is that because of the inclusion of magnetic fields, the cores are slowed down more efficiently, and since the angular momentum is transported from the core and deposited in the surface rotational velocities can remain higher. And that allows us to reproduce both constraints at the same time, which is not possible in the absence of some efficient angular momentum transport process. Okay, we go from the Sun to stars with convective cores, and we can even go to slightly more massive stars. We have the group of stars called slowly pulsating B-type stars, SPB, with masses between 3 and 10 solar masses. And in this case, the problem is slightly more difficult. Massive stars are less abundant and not all of them pulsate. So we only have around 50 stars. And there are some hints by Maygate Pedersen that some additional process is needed to slow down the cores. Now, what happens after the end of the main sequence? Here we have a very important problem, which is the problem that in part we're trying to solve, which is basically that the standard prescription for the magnetic fields that was proposed by Sprout is way too inefficient to reproduce the core rotation rate of red giants. Then there was a recent revision of this theory by Jim Fuller, which allowed to reproduce the core rotation rate of red giants. For example, computing models that can also reproduce the surface rotation rates here by the dashed lines. Sorry, I didn't say it, but the squares are the surface rotation rate of the observations, and the circle the core rotation rates of the subgiants. So the thing is that this new theory can reproduce the red giants, but is too efficient during the subgiant phase. So this is an indication that maybe other theories are needed, or we need to revise some other ingredients of the models. This is for slow rotators. They are computed with initial slow rotation rates, more or less. But when you go to fast rotators, for example, computing models with higher initial velocities in agreement with this group of stars, coming back to this plot. Now, if we include magnetic fields, we can reproduce quite well the connection between the main sequence stars and the red giants. And even more, if we continue the evolution until the core helium burning phase, all the way to the tip of the red giant branch, this drop is because of the helium flash, and then going to the core helium burning phase, this kind of process can reproduce quite well the observations. So I will leave my concluding remarks here. And I would like just to stress out that the current problem is on the subgiant phase, and that even if the magnetic fields generated by the Tyler's Proof dynamo is a quite good candidate, there are other physical processes, so much more theoretical work and modeling work is needed. So that's it. Thank you very much.
So can your model explain the low lithium abundance in the sun?
Yes. There is a paper by Patrick Eggenberger from 2022 in Nature, and they demonstrated that both the solar rotation profile, the abundance of lithium, and the abundance of helium can be reproduced with these kind of models.
Hi, very nice work. I have a question. When you mean magnetic field, you are talking about which range of intensity? Of course, that depends on the range, I suppose.
Yeah, that's a great question. So the radial magnetic fields in this process are quite weak. In most of the cases, they are below 1 Gauss. And the azimuthal magnetic fields are on the order of 1 kilogauss to 10 kilogauss. This is because the radial fields are quickly transformed into azimuthal fields because of the omega effect.
Okay, and the second question is, when you show that the evolution tracks fit quite well your data, that implies that all stars are magnetic.
Yes, so there is some theoretical work going on.
No, I'm not afraid, but that will be the conclusion.
At least in the core, we expect to have azimuthal magnetic fields, yes. There are no observations yet demonstrating that, but there are some measurements from mass seismology in the core of red giants that there are strong magnetic fields in the cores.
Okay, and one final question. Maybe you said it already, but in the surface, you predict which intensity of magnetic field, those that you mentioned, or those were at the core?
Well, the process should operate in all radiative regions. So if the star has a radiative envelope, I would expect to have rather low radial magnetic fields, but strong azimuthal magnetic fields.
Thanks, really nice work and really nice talk. Since you put the white dwarfs there, I'm going to ask if your model does extend there, if you can explain the white dwarfs as well.
Yes, I didn't compute that model until the white dwarf phase, but I think that I have a extra slide here by Jim Fuller. This is from the paper of Fuller. Well, they took the evolution until the white dwarf phase for different initial masses. So on the y-axis, what I show is the rotation period of the white dwarf in hours, and the x-axis, the mass of the white dwarf. And these points are just data points, and well, the model in red. So yes, overall, the rotational periods of white dwarfs can be reproduced.
Thanks.
One more question.
What are the implications for things like age determinations of young clusters when you use these massive stars?
I never look at that point, but I would expect to have lower ages overall, I think, because of the fact that when these kind of processes are included, the evolution goes towards the bluer part of the age diagrams. So I will expect that from the isochron fitting, the ages will be lower.
Yeah, I mean, if you apply standard isochrons now, I would think you would get older ages because it looked like they were evolving off the 0-age main sequence, right? Or moving away from 0-age main sequence in your models.
I think so, yes. I have to look at that a bit more in detail, but we can chat later.
Yeah, okay.
Okay, we have no more time, but thank you, Facundo. Muchas gracias. And nuestro próximo orador es Javier Alonso-García. Y he's going to tell us about pulsating stars in the inner galactic VVV globular clusters.
Bueno, en primer lugar, agradecer a los organizadores la posibilidad de poder hablarles sobre el trabajo que estamos haciendo. buscando las estrellas variables en los cúmulos globulares que se encuentran hacia el interior de la Vía Láctea. Y especialmente interesantes van a ser las estrellas pulsantes, porque algunas de ellas, como las RRLA, son comunes en los cúmulos globulares y además nos van a ayudar a caracterizar mejor estos cúmulos. Okay. So first of all, let me start by reminding you that there are around 166 globular clusters well known in the Milky Way, according to the last or the most recent Vanguard compilation. In addition to that, there are tens of candidates that Dante Miniti or Elisa Garro or Tali Palma or Felipe Gran and other people working with the VVV data have been finding. Sorry. And as you can see from this compilation, there are like a big number or most of the distribution of the stars is concentrated towards the center of the Milky Way. So this presents a challenge because mainly for two reasons. The first one is high extinction. So when you look towards the inner Milky Way, extinction is starting to get higher and higher. The other thing is the big number of the significant density of field stars present there, which is going to also difficult our studies. So in order to try to fix the problem of the extinction, we can go and try to look in the near infrared. Just remember that in the near infrared, the extinction in the KS filter is 1/10 of the extinction in the optical B. So for this, the VVV survey, which is a survey in the near infrared for the galactic bolts and the galactic plane, is going to prove very useful for our studies. Okay, so of the 166 clusters in the globular clusters in the Vanguard compilation, there are 41 of those that are in the VVV footprint, and there are 22 more that are in the VVV extended footprint too. So a big number of the globular clusters in our Milky Way are located there. So they are still just remember, these clusters are going to be the ones that are worst characterized because of the problems that I just mentioned, extinction and high density of stars in the field. Their characteristics are not so well known as the ones in the galactic halo. Okay, so if even in the near infrared, when we try to plot the color magnitude diagrams, this is up to the tidal radius of the globular clusters, you can see that they are a mess. The sequence, the RGB sequence of the cluster is mixed with the RGB of the bulge. There is also the main sequence for the disk there. It's very difficult to study the globular clusters there. Even if you go, a little deeper, a little closer to the cluster, this is up to 1 arc minute from the center of the cluster, there is still, a significant number of stars in the field. And even if you try to use other methods to decontaminate the field, like using proper motions, well, the problem is that you still have you are gonna end up with very few stars, or even there is significant differential extinction there. So the CNDs, the color magnitude diagrams, are not going to provide us with very nice or with very good characteristics for the clusters. The study of these CMDs is not so good. So is there anything that we can do? So here is where the second V in the VVV becomes very useful, the V of variability. And we can try to look or to find this information for the clusters using the variables present, okay? So in order to do that, we have been working with, in the last years, with the preliminary version of VIRAC, which is a catalog, a photometric catalog of the observations of the VVV that is going to provide us, well, and is based on PSF photometry, okay? So VIRAC2 not only provides us with the light curves for all the stars in the VVV, but also provide us with different statistics of the photometry, and also it provides us with the proper motions. Okay, so using VIRAC, we first look at the stars that are inside of the tidal radius of the globular cluster and that are in the VIRAC catalog. And then the next thing that our method to find variables does is we just look at the variation of the magnitudes at the different epochs that we have from the VVV, and just take, well, the variables are going to have the biggest deviation at a given magnitude. Okay, so we just keep the stars with the biggest deviation. Then we submit those to a generalized Lomme-Scargol algorithm to find the best period. We phase the curve. We submit that to a Fourier fit and find the raw parameter. The raw parameter is the deviation, is the ratio of the deviation of the distribution of the K magnitudes in the different epochs from the Fourier fit. Basically, what you should know is that a big raw fit, a big raw parameter, like in here around 9, gives you a nice variable. A small raw is gonna give you like, you know, it's more difficult to say that that star is a variable. So with this parameter, we are able to, or with this analysis, we are able to find the best variable, the best variables that are in the field of the globular cluster. So the next thing, we are able to find RRLA in the fundamental mode, in the first mode, type 2 Cepheids, you know, even eclipsing binaries. So then the next thing is to say, okay, so which of them belongs to the cluster? And for that, we just assign membership just by visual inspection, by machine learning, also, you know, and for that, we look at the position in the sky, we look at the proper motions, and we look at the positions in the color magnitude diagram. Okay. So an interesting byproduct that I should make, let me make a small digression here. A nice byproduct of our method is that we can also calculate the proper motion of the globular clusters. And we find that for most of them, the results agree very well with Gaia, but for some of them, there is a significant offset, mainly for the most extinct ones, the ones that has a higher extinction. Why? And you can see that our results are kind of obvious. You know that the cluster is around here, and this is significantly different from what Gaia says. Why is this happening? Well, the problem is that Gaia probably is not seeing this cluster. So they are just saying that the stars that they are finding, they are not members of the cluster, and we are able to see them. Okay, so coming back to our result, or to our method, we just have for characterizing the cluster, we just get the properties of the cluster using the RRLA-LARIM that are present in the cluster. We have a new color period luminosity metallicity relations for these clusters that have been calibrated with the Vista in the Vista system, and we are obtaining the results, new values for the extinction and for the metallicity for extinction and distances to these objects. In most of the cases, again, we agree quite well with the literature, but for some other, especially for the most extinct clusters, our results are significantly different. But again, this is mainly because previous works have been limited by extinction or by the number by confusion with other field stars. Two last points here. One interesting thing for the clusters which present a significant differential extinction in their fields, our method is very nice because we don't need to assume an extinction law. We can get it from the data, from the RRLA-LARIM. We just plot the extinction versus the distance modulus, and the slope is going to give us the extinction ratio, and the 0 point is going to give us the distance to the object. So with 1 fit, we can get the extinction law and we can get the distance. One last thing, there are in some of for some of these clusters, there are also Cepheids in the clusters, type 2 Cepheids. So we can use their own period luminosity relation to find independently from the RRLA-LARIM the distance to these objects. And as you can see there, the agreement between both Cepheid and RRLA-LARIM results is very good. So this is like an independent way to see that our results are quite all right. Finally, let me end by reminding you again that there were like 41 globular clusters in the VVV survey. We have looked only to a few of them, so we intend to look to all of the ones that have RRLA-LARIMs there. Also, there are 22 more in the VVVX. We are going to look then in the near future. So if you are interested in this field, just please stay tuned for new results. Thank you.
Ok, gracias Javier. ¿Preguntas para Javier? Oh. Tenemos tiempo.
Thanks, Javier. The discrepancies with the Gaia proper motions, is it just that Gaia doesn't see the cluster, or is it that the membership is not properly assigned so that you get a mix of field and cluster stars?
I think. Okay. Sorry. I think that it's mainly because Gaia, the stars that Gaia identify as members of the cluster, they are not really members of the cluster, because Gaia is the problem is that Gaia is not able to see them because it's so extinct. The extinction there is so high that Gaia doesn't reach.
Okay, so the whoever associated these things with the cluster, they did it just by the sky position or something, or
I guess that they try to look at the position where the cluster is, and they try to select somehow the stars, but they couldn't see them. So
So just one more bit self-serving question, but a Gaia version in the infrared, is that something that you would be happy about?
That's something that some people are talking about. There is a project with the Roman telescope, with the Roman Space Telescope, to observe these regions of the bulge and the plane, and maybe in the future we will have that would be idea. Yeah.
Okay, thanks.
Bueno, ya tenemos, Dante quería hacer un comentario, creo, una preguntita, y con eso, allá.
No, just a small detail, technical question. When you compute the magnitudes, the mean magnitudes to infer the distance, you use the average magnitude, you use the magnitude and minimum light?
No, I use the weight, so it's the intensity, weight, magnitude.
Bueno, estamos en tiempo ya, así que agradecemos a Javier y a todos los que presentaron en la mañana. Llegamos a ser finalizada la sesión.